What we have here is an airplane with a swept wing, known in English as a swept wing. You've been asking for this for months, which is why we're here. Welcome to this channel, Science Junkie. I'm Sergio Hidalgo, an aerospace engineer, and today I'm going to tell you the main reason why all commercial airplanes, to this day, all of them without exception have a swept wing design. Commercial airplanes and fighter jets share the same design where the engines are located under the wings. And besides, there are other airplanes that can change this angle in mid-flight, like the Panavia Tornado, the F-14, and the Tupolev 166, and honestly, there are quite a few more. This also explains why some aircraft can alter their wing geometry during flight. So let's get to it. The first thing is to understand why and when swept wing designs started to appear. I think the clearest example that can help us understand this perfectly is if we look, for example, at the X-1, the experimental aircraft that broke the sound barrier, and then we look at the X-2, its bigger brother. The X-1 successfully broke the sound barrier. But when it approached transonic speeds, when it was going at Mach 0.90 something, the plane started to shake in an incredible way. In fact, it managed to fly at supersonic speeds, but it didn't go much above Mach 1. However, the X-2, the older brother, flew up to Mach 3. You don't have to be very smart to notice that the X-1 has straight wings, however the X-2 has swept wings. Let's see why. What we have here is an X-5 plane, capable of changing the wing geometry in mid-flight. It was the first experimental plane capable of this. Let's discuss it further. But, as you may already know, airplane wings make the air on top accelerate. If a plane flies close to the speed of sound, like at Mach 0.9, the air accelerating over the top could go supersonic, causing shock waves to appear. Of course, as the plane keeps accelerating, the region with supersonic flow gets bigger and the shock wave moves backward. The intensity escalated with each occurrence, significantly increasing aerodynamic resistance and drag. But not only that, it also greatly increases instability because the air might separate after the shock wave. And this causes the distribution of lift force on the wing to change, so the plane starts to move very abruptly. So by giving the wing a sweep angle, what we do is make the wing chord no longer parallel to the direction of the air, but instead there is a small angle. This results in two velocity components. If we look at it in this coordinate system, one would be parallel to the chord, and the other would be perpendicular to the chord, meaning it would go in the direction of the wing. And this is where the key to everything comes in, because the air only accelerates in the direction of the chord. So now that speed is going to be the speed at which the plane is moving. The red arrow multiplied by the angle's cosine. So the greater the sweep angle of the plane, the lower the speed at which the wing is crossed, that is, in the direction of the chord. However, the smaller the sweep angle of the wing, the greater the speed that is passing through the wing, in the direction of the chord. The most extreme case would be straight wings, where all the air is passing in the direction of the chord, but giving the wings an angle also has consequences for the stability of the airplane. For example, if we look at the X-5, which as I told you was the first airplane that had the ability to change the geometry of its wings in mid-flight, and we see that the lift force would be applied at this point. When we change the angle of the wings, the point where the lift force is applied changes because the wing is moving. And that's why swept wings were already being used even before World War I because of the stability issue. But it wasn't until World War II when there were already very powerful engines and planes were flying practically at transonic speeds that they realized that angling the wings made the shock wave over the wing appear later. In other words, the plane could go faster without the shock wave appearing. As it's always said, necessity is the mother of invention, because it wasn't until they needed it that they actually discovered it. And this is the main reason why it's still used today. For example, a Boeing 747, which has a high wing sweep angle, can fly at pretty high Mach numbers. If it weren't for this, it would be completely impossible. Shockwaves would appear much earlier. If you already knew about swept wings, there's likely another explanation you're aware of. Look, before realizing that angling the wings helped with the wave issue with what happens above the wing, they simply reduced the thickness of the airfoil to be used. Because the thicker the airfoil, the faster the air has to go to get around the top. The thicker the material, the less it affects the air. This example makes it easy to understand. Imagine we have a cylinder and the air is passing over it. If the cylinder is straight, the air will see a circle. However, if we now give it a certain sweep angle, for the cylinder, the air will now encounter an ellipse rather than a circle, while the maximum thickness remains unchanged. What happens is that the shape the air sees now has been stretched a bit, so it has more time to adapt to the geometry of the cylinder. Well, that's how Anderson explains it in his book, that when wings are given an angle, what happens is that actually the air sees a more elongated shape which has the same maximum thickness. Therefore, it has more time to adapt and doesn't have to drastically change its speed. But not everything is good when it comes to the design of swept wings. In fact, it has many drawbacks, but the worst of all, without a doubt, is that the same thing applies at high Mach numbers. This thing about the speed over the wing being related to the cosine of the angle also applies at low speeds. So when a plane wants to take off at 300 kilometers per hour, the wing is actually seeing that the air is passing over it more slowly. Therefore, when you sweep the wing, the plane will either have to give it more angle of attack to get the same lift or go faster to get the same lift. In modern aircraft, this is addressed by incorporating flaps and slats. It has several drawbacks, but this is definitely the worst. We'll discuss the others in a future video. So, what I told you about shock waves above the wing can be summed up in this National Aeronautics and Space Administration graph, where the x-axis is the Mach number at which the plane is flying, and the axis I represents aerodynamic efficiency, which is lift divided by drag, resistance. And as we can see, when you go very slow to have good aerodynamic efficiency, straight wings are the best, but when we get close to Mach 1, shock waves start to form on the straight wing, and the efficiency drops incredibly. Conversely, swept wings are most efficient at supersonic speeds, while straight wings are more efficient at subsonic speeds. And that's why it's a super interesting option to have a plane that can change its geometry in flight. When you're flying at subsonic speeds, you use straight wings, and when you accelerate, when you enter transonic and supersonic regimes, you switch to swept wings. And the first experimental plane used to really study this was the National Aeronautics and Space Administration X-5. Careful, I'm not alone today. Marcos from Mundo de Aviación is here, and he'll give us a brief intro to this plane.
Thank you, Sergio, for giving me space on your channel. I love explaining the history of aircraft development on my own channel. In this case, I'll tell you something about the Bell X-5, which, as Sergio said, is the first plane that could change the geometry of its wings in mid-flight. Its roots originated in the German design of the Messerschmitt P1101, from which the X-5 borrowed a lot in terms of overall design. The Messerschmitt P1101 was considered the ancestor of variable geometry wing aircraft, since it could vary its wings at a sweep angle from 30 to 45 degrees. But only on the ground before flight, to study the aircraft's behavior in different configurations and to seek the greatest efficiency in flight. At the end of World War II, the American infantry discovered a complex where a single prototype was kept, and they also captured all the documents related to the study of variable geometry wings. This single prototype was incomplete and was given to Bell to continue the study. From there, the project that would become the Bell X-5 was born. The design was much more complex than the 101, with 3 wing position angles of 20, 30 and 60 degrees. They could indeed change in mid-flight, using an electric motor system that the pilot controlled from the cockpit. This technology was key for future designs of the Cold War era, such as the General Dynamics F-111 Aardvark, the Grumman F-14 Tomcat and the Rockwell B-1 Lancer. During its test flights, it showed a lot of instability during turns, and because of this, one of the prototypes even suffered a serious accident on October 14, 1953, where its pilot did not survive. The test continued with a single demonstrator, which flew until 1958. To learn more about this fascinating aircraft, visit my channel, Mundo de Aviación.
Another great advantage of being able to change the wing sweep angle in mid-flight is that you can change the aspect ratio. If you don't know what aspect ratio is, don't worry, because it's not a big deal. It's simply a value that represents the wingspan of the plane in relation to the width of its chord. So for example, a glider has a very large aspect ratio because it has a big wingspan and a very small chord. The F-104, for instance, has a very low aspect ratio due to its small wingspan and relatively large chord. So when we compare two airplanes, one that has a high aspect ratio and another that has a low aspect ratio, but both have the same wing area, that is, they're just arranging that area differently. One is stretching it out a lot, having a large wingspan but a short chord, and the other has a much wider chord and less wingspan. Well, when we compare these two planes, the distribution of lift force isn't the same, even at the same angle of attack. A plane with a high aspect ratio generates much more lift than a plane with a low aspect ratio. And that's why gliders have a high aspect ratio, so they can generate a lot of lift force even when flying at low angles of attack. This is why the F-14 would extend its wings before taking off from aircraft carriers to maximize the aspect ratio. Then it would fly subsonic with the wings extended, the wings straight, and when it entered the transonic regime, it would sweep the wings back, and at supersonic speeds, well, swept wings as well. This also applies to the B-1, the American bomber, when taking off with a heavy load, as it's a large plane that can carry numerous bombs. So it extends the wings, makes them straight. This gives it a high aspect ratio, and therefore, more lift at low angles of attack. But then, when it enters transonic regimes, it sweeps the wings back, and at supersonic speeds, the wings remain swept. By the way, this swept wing theory also applies to planes that have forward swept wings, like, for example, the X-29, or the Sukhoi 47, which, in fact, Marcos recently made a video about the X-29. I'll leave you a link here. But it's also fair to say that planes with variable geometry have to add a lot of weight because of the mechanism that changes the geometry. So is this the reason why not all planes have it? Because you're adding more weight, more maintenance, you're adding more moving parts that could fail on you in mid-flight, and so on. Well, science junkies, I really hope you enjoyed this video. Both Marcos and I loved being able to make it together. To contact me, you can reach out via Instagram or LinkedIn. Subscribe here, and then you can watch Marcos's video that I leave for you here, where he talks about the X5. As always, science and lead come first.